Good afternoon. Welcome you all to the High Performance Architecture webinar series. My name is Lan Ding, Associate Professor at the UNSW Built Environment, Commander of High Performance Architecture Research Cluster. Before we begin, I would like to show my respect and acknowledge the Bedigo people who are the traditional custodians of the land on which this meeting takes place, and to elders past and present. This is the 7th High Performance Architecture webinar series this year. The speaker is Associate Professor Phillip Oldfield, Head of School at UNSW Built Environment. Professor Phillip's research interests include sustainable design, life cycle thinking, tall building architecture, and climate literacy in architecture education. He is chief investigator on research projects with total funding in the order of $800,000 and author of the Sustainable Tall Building, a Design Primer, published by Routledge. Professor Phillip is a British Science Association Median Fellow and a regular contributor to many journals. In today's webinar, Professor Phillip will present embodied carbon in the built environment. What is it and how can we reduce it? If you have any questions during Professor Phillip's talk, please put it in the chat and Professor Phillip will answer at the end of his talk. Also, just a note, this talk will be recorded. We would appreciate you switch off your video and microphone if you do not wish to be seen in the recording. Over to Professor Phillip.
Thank you so much, Lan, and good afternoon to everybody joining us today. I too would like to acknowledge I'm on Bedigo land today. I would like to highlight that the traditional custodians of the land that I'm on have been caring for the land, the water, the air, the environment for tens of thousands of years before I came here. And I would like to pay my respects to elders both past and present and extend that respect to any Aboriginal or Torres Strait Islanders who are joining us today. It's a real pleasure to be able to talk about this topic, which I know is a really hot topic at the moment. And I do also want to thank my colleague Lan Ding, who has so carefully curated and organised these series of lectures. I think they've been a real highlight of 2022 in the High Performance Architecture cluster. Now, I've been lucky enough to somehow schedule this lecture this week, and this week's been quite an important week globally because it is a week where global population has slowly ticked over the 8 billion people mark. This isn't live, by the way. I've not managed to schedule my lecture to literally the minute that it crosses over, but this is a screen grab from worldometers.com, which uses United Nations data. So effectively 48 hours ago, we went over the 8 billion people mark. As a built environment community, we have a moral, ethical and social obligation to provide healthy, comfortable, safe and sustainable places for all these people to live, work and play in. But it is a challenge. We are catering to a growing population and we're catering to an urbanizing population. Every day, 193,107 people are added to the world's urban populations. That's 1.4 million people per week, or basically the population of Sydney every month is added to the world's cities. How do we accommodate these people in a sustainable way? And as I say, I think, we have an ethical obligation to do so. The verb to build is an intrinsically socially good thing. 1.6 billion people around the world live in inadequate conditions. This is a photo I took from Mumbai, I think about 15 years ago, of the Dharavi area. So according to the United Nations, 1.6 billion people live in inadequate global conditions, inadequate housing, and 1 billion people live in slums. And I think, the construction industry, the architecture industry, the built environment industry has an obligation to build, to provide healthy, safe and sustainable housing for everybody. And building is a societal good. there's few things I can think of that provide a better societal good than to provide these kind of houses and hospitals and schools and more. But at the same time, we have to accept as an industry that to build is often an intrinsic environmental bad. What I mean by that is every square meter we build has a carbon footprint, and that carbon footprint can be quite high. The materials we rely on in our industries have significant and often very negative impacts on the environment. So if we look at, on the left-hand side here, you've got a pie chart. This is a total production of materials globally by weight. And you can see it's dominated by ceramics, and that in turn is dominated by concrete. We use concrete more than any other material with the exception of water. And now we are addicted globally to concrete. Cement, which is the main ingredient in concrete, is estimated to contribute 80% of all human-induced CO2 emissions. Now, to put that into perspective, the aviation industry is about 2.5 to 3%, the much maligned aviation industry. Cement contributes more CO2 emissions than virtually every country apart from America and China. And this I find an amazing statistic that, you know, we are truly in the Anthropocene. You know, we are, as a human race, we have now dominated nature. If we weigh all of our buildings and infrastructure, they now weigh more than all trees and shrubs. That's an amazing statistic. We have now dominated nature. All human-made stuff now weighs more than the biosphere, all natural-made stuff. That's quite incredible. And there's another graphic I quite like, which encapsulates this. This is a visualization of anthropogenic mass. What you're going to see on the right-hand side is all human-made stuff, and at the top it's concrete. Everything grey is concrete. What you're going to see on the left-hand side is all natural-made stuff, global biomass, the dry weight of all life on Earth. I'll put a little animation, hopefully this works. So what you're seeing on the right-hand side, that's concrete. Each square of that is a gigaton. And then you've got bricks, and then you've got aggregates, and then you've got metals, and then you've got asphalt, built environment materials. We use trillions and trillions of tons of these kind of things, and they now dominate what the world is and what the world is made out of. So all plastic, for example, now has double the total weight of the entire animal kingdom. Now, to flip back to the built environment, you know, how can we start to understand some of these statistics within buildings and individual buildings as well? Well, we can use something called life cycle thinking and life cycle analysis. And I'm sure you've all seen diagrams similar to this in the past. If we think about a building or city or group of buildings, they will have an environmental impact across their entire life cycle. So to build that square meter of floor area we talked about before, it might be built out of a steel frame, for example. There might be a steel beam in there. So to create that steel beam, we have to extract iron ore from the ground. We transport that to a factory. That's in the blue area on the left-hand side of this diagram. In that factory, we'd create a steel beam. And then we'd transport that to a construction site. We'd lift that steel beam up to the right floor. Then that square meter of floor area, we would heat, we would cool, we would light it over the cycle of its life. That is a yellow square. At the end of that square meter of floor plate's life, we might demolish it. We might recycle some of the steel or some of the concrete. We might downcycle or send to landfill, for example. At each point in this diagram, carbon emissions are released. And as an industry, we're guilty historically of focusing in just on one part of that, just on the operational part. So what I really want to do today is to open up that diagram and try to understand what some of the other areas are and how significant they are and how we can reduce them. So what is embodied carbon? Well, embodied carbon is the greenhouse gas emissions due to constructing the building and its materials. So the greenhouse gas emissions from extracting the raw materials, processing those materials, assembling the components, transporting those materials around, effectively to make the building, and then to maintain the building, excuse me, and also often to deconstruct and dispose the building at the end of its life, although that's sometimes not included due to the uncertainty around measuring that in the future. And we've got the operational carbon, that's the heating, the cooling, the lighting, and the small loads, plugging in your iPhones and your laptops as well. And if we want to properly understand what impact a building has on the environment, we need to add the two of them together. So we need to add the operational plus the embodied, and we get the life cycle carbon emissions. It's relatively straightforward. Excuse me. And historically, you go back 20 years, when I was starting my PhD out, the historical thinking was, look, our operating emissions are about 80%. Embodied carbon is important, but really it's about 20%. And you can see that in our building regulations, for example. We have relatively mature building regulations around the world that are concerned with operating emissions. We have very few building regulations concerned with embodied emissions. However, what our current thinking now is, it's probably closer to 50-50. Now, why is that? Why has our thinking changed? Well, our building regulations have got stricter, they've got tighter, we've got more energy efficient. To heat, cool and light that square meter floor space, we use less energy now than we did, say, 20 years ago. Better facades, more efficient systems. To do that, often we use more materials. We might have more insulation in the building. We might have solar panels stuck to the building. We've also got better at measuring embodied carbon. We've got better at measuring some of the things that were not measured in the past, the mechanical systems, the facades, the finishes. So really, we're probably at 50-50. But the truly perhaps frightening thing, or thing to be very much aware of, is by 2030, we might be at 0% operating and 100% embodied. So if we are to meet the World Green Building Council's targets, every new building built in 2030 onwards should be net zero or nearly zero operating emissions. So what effectively will have pretty much close to zero operating carbon. And what that will mean is our embodied carbon effectively becomes the total carbon footprint of a building. And that's a pretty big shift. And if I look at an architecture student joining the program in my school next year, they will spend 3 years in their undergraduate. They might go out and work for a year, then they'll come back and do 2 more years in their masters, then they'll work a bit more. By the time they become an accredited architect, it will be 2030. They'll be moving into an industry that has, where the understanding of what our carbon emissions are will have totally transformed in 10 to 15 years. And they require a totally different way of understanding, measuring and changing the carbon footprint of our buildings. So this is all happening very, very quick. Here's a good example, which I've kind of calculated. If this year, 2020, we build a brand new Neighbours 5.5-star office building in Sydney, we build it in 2022, and we're going to measure all its carbon emissions all the way to 2072. That's what you can kind of see here. And what we can see in 2022, we build the building, and that has a big upfront embodied carbon. You've got to make the concrete, the steel, the triple glazing, whatever, all the solar panels on there, whatever. I'm estimating that would be about 1,800 kilograms of CO2 per square meter. And then day one, the building opens, you turn the lights on, you turn the air conditioning on, and then you've got the red line. And over time, the red line builds up and accumulates. That's the operating emissions. That's the heating, the cooling, and the lighting. But what you can see is that red line is not linear. That red line is curving. And the reason that red line is curving is because over time we're decarbonizing our grids as well, which is a good thing. But it does mean that when we consider the whole life cycle footprint of a new building built in 2022, what we can see in the pie chart on the right-hand side is the embodied emissions make up the majority of the building's carbon footprint. In this case, about 2/3. Now, this is a low energy building and a high embodied carbon building. So sometimes it might be 50-50. But the key message I'm trying to get across here is embodied carbon is significant, and it's far more significant than it was only a few, 3 or 4 years ago. Our understanding of where a building's carbon emissions come from has changed, and it's changed very quickly. And we're still behind in terms of the regulatory and methodological frameworks to kind of measure this and to change it. So against this backdrop as well, you know, as I mentioned before, we're building more than ever before globally. So current projections on future growth of buildings are effectively we're building the equivalent of every building in Japan every year. So if you take the entire floor area of Japan, all the building stock, we're building that every year. 2022, we're building Japan. 2023, we're building Japan. 2024, we're building Japan. So we are set to build all the buildings in Japan every year for the next 38 years. What's the carbon impact of that? How many thousands and millions of tons of CO2 emissions could that be? And how will that impact our aim to limit global heating to below 1.5 degrees? It's relatively easy to do the math around this. What you can see on the left-hand side here is a table, and this table is taken from the IPCC SIF report. And this table talks about the carbon budget. Effectively, carbon emissions are cumulative, excuse me. And so we have a remaining carbon budget, which we cannot exceed to keep global temperatures within 1.5 degrees. And if we want a 50% statistical chance of maintaining 1.5 degrees, our remaining carbon budget is 500 gigatons. And you can see that I've highlighted that in red. If you want an 83% chance, it's 300 gigatons. You want a 17% chance, it's 900 gigatons. So it depends on what chance you want. Let's just say a 50% chance. So we've got a remaining carbon budget of 500 gigatons, and we're going to build 230 billion square meters of floor area globally. So let's assume we build all that floor area to the standard Australian detached house. And the standard Australian detached house, I know, is about 660 kilograms of embodied carbon, kilograms of CO2 per square meter. So we've got a very simple piece of math. We can take 230 billion square meters, we multiply that by 660 kilograms of CO2 equivalent, and the embodied carbon of all those new buildings will be 151.8 gigatons of CO2. That's 30% of our remaining carbon budget. So if we just build all future buildings to the standard Australian detached house, we would nail 30% of our future carbon budget before we turn the light switch on, before we drive a single kilometre, before we retrofit any other building, before we grow anything, before we eat anything, before we do anything else. 30% of our emissions, of what we allowed, what allowable future emissions have gone. And for me, that's unviable. That's unviable. That tells me we cannot continue along the path we are on. At the moment, it's 10%, typically, that we think 10% of global emissions are from the construction industry. But if we carry on like this, it could be 30%, just at the time we need to reduce. And this brings to me what I call the embodied carbon contradiction. And this graph is from the 2022 UNEP Global Status Report. What you can see there, the red dots are billions of square meters of floor area. So we're going to double global floor area. During the same time, we get building related emissions down to zero. And I think that's a contradiction. I think that breaks the laws of thermodynamics. How can you double what you've got while using basically zero or very close to zero emissions? And I think that says we've really got to fundamentally change how we build, how much we build, the way we build, and our thinking around building as well. That's what I really want to talk about in today's discussion. And against this backdrop, many of you will have seen this report. I think it's from about 2018. It's called Bringing Embodied Carbon Up Front from the World Green Building Council. And for me, it's the first global recognition of embodied carbon as a major challenge. And it sets two targets, which I think are really important. By 2030, all new buildings, infrastructure and renovation will have at least 40% less embodied carbon. By 2050, new buildings, infrastructure and renovations will have net zero embodied carbon. So they're the two targets, 40% reduction in the next 7 years, and then down to net zero by 2050. How do we get there? Well, there's 4 main mechanisms that the report articulates. Firstly, build nothing. Secondly, build less. Thirdly, build clever. Fourthly, build efficiently. And the key learning here is that build nothing or build less is better than building clever or building efficiently. The greatest savings of embodied carbon can usually be realized at the earliest stages of a project. So I want to spend the next 25 minutes going through the first of these: build nothing, build less, and build clever. I'm going to build on some other people's research and also show 2 projects I've been lucky enough to be involved in, particularly around the build clever side of things. It's pretty controversial because, as I started my presentation by saying earlier, we can't build nothing. We have a societal obligation to build, to improve people's lives. But it still means we are allowed to question when we build, and I think we do need to do that a little bit more. And this is a bit of a controversial, provocative kind of attempt by me, just to get everyone thinking. This is a bit of a thought experiment. After the last census in 2017, so the census was 2016, this newspaper article came out which said 1 million homes are left empty across Australia. Now I know in reality 1 million homes are not left empty. You know, the census didn't pick that up for a number of socioeconomic reasons. People were just out, people were on holiday, houses weren't being rented for whatever reason. But let's just do a thought experiment. Let's say 1 million homes were left empty across Australia and we could better occupy them. What would be the embodied carbon saving of not building 1 million homes? Well, 1 million homes, an average of 230 square meters, typical embodied carbon of 660 kilograms of CO2, you would save 152 million tons of carbon dioxide. Now, again, I stress, I know 1 million homes are not necessarily left empty. But even if it was 100,000 homes, we could better occupy. That'd be 15.2 million tons of carbon savings. So fundamentally, we do need to build, but we also need to question when we need to build and how we can make better use of our existing building stock as well. Life cycle thinking also allows us to question when we should build too. And we've always got to recognize as societal goods and environmental challenges. But this is a really good example. This is Crossrail in London. And Crossrail is one of the most significant major infrastructure construction projects in the UK. I think it opened this year. Anyone who's ever lived in London, getting from east to west is a bit of a nightmare. The central line is at capacity, so it's a new east to west connection across London. And it's a significant amount of construction, 10 years of construction, several new stations, massive amount of infrastructure that will improve people's lives. Life cycle thinking, though, gives us the metrics and the methodology to calculate the environmental gains and losses of something like this. And this graph tries to explain it. So to build Crossrail, the embodied carbon was 1.7 million tons of CO2. And so you start with a negative. You start by having invested and used 1.7 million tons of CO2. Now, because you've built a new public infrastructure, you're hoping people are going to leave their cars at home, they're going to catch a train. And you're hoping people are not going to get the dirty old diesel trains, they're going to get the new electric low carbon Crossrail system. And so you will have accumulating over time carbon benefits. And the red line and the green line show that. So in the best case scenario, Crossrail would save 225,000 tons of CO2 per year. That's if lots of people get Crossrail and they leave their cars at home, you know, more people commuting via low carbon public transit. Now, if the building is built in 2022, that best case scenario will take 8 years to get the carbon back, to get effectively to offset the initial embodied carbon. So that building, sorry, the Crossrail will be in carbon deficit until 2030. seems pretty reasonable to me. You've got a pretty reasonable buyback. In the worst case scenario, it's only 70,000 tonnes of CO2 per year. And so your worst case scenario is about 24 years. And so Crossrail would be in carbon deficit until 2046. And that seems far less reasonable to me. And so what we're left with here is making a decision about, should we build infrastructure like this, pending the environmental benefits and disbenefits. We've always got to factor in as well the societal benefits as well. This is going to improve people's lives, it's going to improve productivity, it's going to improve health and well-being as well. There's pollution taking cars off the road. So I'm not suggesting we don't build infrastructure like this, but you start to ask, you know, would it be better to have electric buses rather than a major construction like this? And I don't know the answer. I'm merely provoking the kind of questions and really articulating that life cycle analysis and embodied carbon calculations give us a tool to dig into that, to explore those options. So we've looked to build nothing, which is not really an option in many cases, but could be. Let's look at build less. And that will give you up to an 80% reduction of carbon emissions. And build less really talks about retrofit and over demolish rebuild. And that's been, you know, celebrated by Pritzker Prize winning architect Lacton Vassal, whose kind of mantra is never demolish, add, transform and reuse, really promoting this idea that architecture needs to shift from building new buildings to firstly looking at retrofit and reuse. And we're starting to see this happen more in developments as well. So the Olympics used to be slightly renowned for building all new buildings, which, you know, their legacy was sometimes quite questionable. And we're seeing in Paris 2024, Los Angeles 2028, there's a shift around from building new buildings to retrofitting and updating existing buildings and building temporary buildings. So Los Angeles 2028, the kind of master plan, its mantra is called radical reuse. So Los Angeles can host the 2028 Olympic and Paralympic Games without building a single new permanent venue. We were fond of saying during the bid phase, and it remains true, the most sustainable venue is the one you don't have to build. Again, it's not always possible in every place around the world, but certainly where there is the existing sports infrastructure, do we need to build new sports infrastructure? Or can we retrofit the one we already have? And I think, you know, some fantastic examples of this on our own doorstep. I know I wax lyrical a little bit about the Key Quarter Tower by 3XN and BVN, but I do think it is the most important, or one of the most important tall buildings of the 21st century. The radical upcycling of a 1970s office block to almost double the floor area, but to save around 7,500 tons of CO2 as well. And it's quite the construction feat as well. So all credit to the architects, to the developer, to the contractor and everyone. It's quite an amazing project. And you know, I did the numbers around this as well. There are 1,000 tall buildings around the world that are over 50 years old, office buildings. And therefore I think 1,000 buildings at risk of being demolished. What better way to save carbon emissions, to do something like this, to upcycle them into a more contemporary, more efficient and more spectacular kind of piece of architecture on the skyline as well. We also need to build towards a circular economy. Our current industry is incredibly linear. We take materials, we build, we demolish, take new materials, we build again. And so moving towards a circular economy in our industry is vital. This is one of my favorite examples of it. It's called Resource Rose in Copenhagen. We all love recycled brick, but it's incredibly energy intensive and cost intensive to cut the bricks back out of the mortar. So all they did with Resource Rose is there were some existing industrial buildings on site. They got a circular saw and cut patches of his buildings out and basically hung it as rain screen cladding. And you can like the architecture or you can not like the architecture, but it's an incredible reuse of existing materials. And really, I think we should start looking at our existing building stock as a resource for new materials. Buildings as material banks, potentially. In Holland, they're quite far ahead in this regard. So in Holland, you know, they're probably at the cutting edge of the circular economy, and they've mapped where all materials come from into the built environment and where they all go, which is an incredible feat of research. And this is a diagram, a fantastic Sankey diagram that tells the story. And what they found in Holland in their circularity report is that 88% of demolition waste was recycled. And that's great, but most of it was downcycled. Most of it was, you know, concrete was crushed up and made into aggregates to put under roads. Most of it went into infrastructure. When they looked at the materials going into construction, they found only 8% were recycled materials and only 4% were renewable materials, basically biomaterials, natural materials. And they meant 88% of materials going into the system were virgin materials, were new materials. So while a lot of materials was being recycled, it was being downcycled. What the circular economy commands us to do is to upcycle materials, to make sure they're as useful as the original materials, so they can live a number of useful lives. And really, you know, call me slightly utopian, if you will, but I see a future, and I'm convinced there has to be a future where we consider buildings not as the kind of the resting place of our materials, as the final resting place of our materials. We consider buildings as a temporary, long-term resting place of our materials. So if you put a piece of cladding on a building now, you know, the building owns the cladding. The cladding is designed to stay there for all its life. What if it didn't? What if the building was rented the cladding? What if it loaned or borrowed the cladding for 20, for 40 years? And then at the end of the cladding's life, it was given back to the original manufacturer and reused, recycled, and could be turned into something else. Now, I realize that might be slightly naive and will require changes to industry, society, economics. It will require companies that still last 40 years. But really, it's those socio kind of structural moves that we need to happen if we are going to actively see a circular economy in our built environment. Checking time. The third thing I want to talk about is build clever. And here you've got up to a 50% reduction of embodied carbon. And I see our buildings today as, you know, this is a bit of an analogy, but like a cast. You break your wrist, you wrap a cast around it, and it's pretty effective for keeping the wrist still. It's very effective, it's very functional. Sometimes it gets a bit itchy, you've got to stick a pencil in there a little bit. What I'm interested in our buildings becoming is more like this. Do we need all that material? How can we quite radically question what we need and what we don't need to change current paradigms? I was lucky enough last year to get a tour of William Smart's office. I'm sure many of you might have seen it. It's adaptive reuse of a 19th century industrial space. And what amazed me is how delicate and thin the steelwork was. And the reason was, when it was built, materials were incredibly expensive and valuable, but labor was cheap. So you spent a lot of time really minimizing the amount of material that went into a building, really dematerializing the building to make it efficient, to make it economic. And today, kind of the opposite is true. Materials, concrete's pretty cheap. We can just put a big 200 mil thick concrete slab to create a floor slab, and labor is very expensive. So we really have to minimize, looking to minimize the labor to make things economic rather than maximize the materials, because materials are cheaper effectively, although that's perhaps starting to change. And I'm really fascinated to see innovative new material developments and product developments like this. This is a mini-mass hybrid beam. And what it does is it questions, we've got a 500 mil deep concrete beam. We don't need all that material. You know, some of that material is redundant. If we cut out all the material we don't need, we can save 78% material weight. And I think that kind of innovation, although it might be more labor intensive and thought intensive in the upfront, as it becomes more commonplace, could really dramatically dematerialize a lot of our built environment. And I want to give an example as well about just how significant dematerialization can be. This is the Shanghai Tower by Gensler, built several years ago now in Shanghai. It's a 632 meter tall building. If anyone wants to talk to me about whether a 632 meter tall building is sustainable or not, you can catch me later. I won't go into it now. But effectively, when you build that tall, huge lateral wind loads pushing on a building. So what they did is they went for a structural optimization program to reduce the wind pressure on the building. And in the end, they found a 120-degree twist of the building, reduce the wind loads the most, reduce the wind loads by 24%. What that did as well is it reduced structural materials by 32%. It reduced the amount of materials by 20,000 tons of steel. That had a triple benefit as well: reduced wind loads, reduced materials, also saved $58 million US dollars from the construction cost. Benefit all round. It's worth pausing just for a moment though to think, what is 20,000 tons of steel? What kind of saving is that? If you do the analysis like I did, you'll see that 20,000 tons of steel is about 42,000 tons of carbon dioxide. Now, the top of that building, it's got some wind turbines, and they rotate and they generate low carbon energy. Those wind turbines would have to turn for 358 years to offset the same amount of carbon emissions as was offset by dematerializing the structure. And the reason I show this is just to show the very significant impact of embodied carbon savings, as opposed to, say, sticking on some green bling technologies onto the top of the building. It also means we've got to very carefully question what we do in a building. And again, I'm going to come back to that societal good, environmental bad kind of analogy. This is the Inteso San Paolo Tower in Turin. It's by celebrated architect Renzo Piano. And it does what a lot of tall buildings in Sydney and around the world do. It tries to open up the ground floor for a public plaza. Now, to do that, it transfers all the structure out using that transfer truss, that big red transfer truss, pretty significant piece of engineering. That transfer truss is 2,350 tons. That has an embodied carbon of 6,815 tons. My question here, and I don't know the answer, is it worth it? Is that environmental cost of nearly 7,000 tons of carbon dioxide worth the opening up of that public space at the bottom? Perhaps it is, perhaps it's not, but we need to be having the discussions and doing the calculations and having the qualitative and quantitative analysis to really understand if the decisions we're making like this are the right ones for society and the environment. Now, I bet you came into this kind of presentation, you didn't think you'd get a lecture on healthy eating, but here you go. This is the food pyramid. And basically what the food pyramid says is to have a healthy diet, you need to eat more of the foods at the bottom of the pyramid and fewer at the top. So more vegetables, more salads and fruit, more wholemeal cereals and breads and potato, and less sugary drinks, fat and salt. So to have a balanced diet, more from the bottom, less from the top. And I think, like a balanced diet, we need a balanced material palette in the built environment. If we were to look at an example of a building material pyramid that uses the same kind of analogy, this is by the Royal Danish University. This is their materials pyramid. Materials at the top have a very high embodied carbon, materials at the bottom have a far lower embodied carbon. And I would never say we can't use the materials at the top. We need aluminium, we need steel, we need zinc. But much like a balanced diet, we need to better balance our material usage across the built environment. We need to use more materials from the bottom, more low carbon and biomaterials, and fewer materials at the top. And biomaterials are very interesting. I think there's a huge opportunity for us to start to transform our built environment using biomaterials. And you can see timber, this is International House by Sands on the left, and you can see even cork and some quite innovative materials. You've seen cork, you know, there's cob, there's all sorts of interesting materials as well. And the thing about biomaterials, effectively, you either dig materials out of the ground or you grow them. That's where materials come from. There's no other option. And if you think about concrete, concrete is intrinsically emits carbon emissions. So when you make concrete, you heat up limestone in a kiln and it releases CO2. Biomaterials do the opposite. When you grow a tree, it absorbs CO2. And you can take some of that benefit and allocate it to a building. So the first project I want to talk about, I'm going to speed up a little bit because I've only got about 10 minutes left, is called the Carbon Value Engineering Project. And this was a project funded by the CRC for Low Carbon Living. It was a collaboration between UNSW and Multiplex. And effectively, this project set out to look at the cost of buildings and their embodied carbon, how we could bring the cost down and the embodied carbon simultaneously. One of the things we did is we took a multiplex building and we modeled it to determine its embodied carbon. Then we looked at lots of different options to reduce the cost and to reduce the embodied carbon as well. So you can see the building on the left-hand side. It had 5 stories of basement, concrete basement, and then 13 stories above ground. And it had an embodied carbon, we found, of about 750 kilograms of CO2 per square meter. Now, if we change that building to a post-tension slab, we saved 8% of embodied carbon. If we changed it to a CLT and concrete hybrid, we saved about 16%. But if we move to an entirely timber structure with a concrete core, we save between 18 to 32% of the carbon emissions, so embodied carbon emissions. And you never know by looking at the building from the outside. The building stayed exactly the same GFA, same NLA, same cladding, just changing the structure saved up to 32% of embodied carbon emissions. So I'm going to end with one more project because I've got about 5 minutes left. I'm asking the question here, so can we get down to net zero in Australia? And that's net zero embodied and operational. This was a project funded by the Digital Futures Institute. It was led by Cameron Allen and Tommy Weidman, with collaborators from UNSW, Monash, UTS, CSIRO, etc. We had 3 or 4 aims. Firstly, we wanted to model the Australian built environment sector between 1990 and 2050. That's all commercial buildings, all residential buildings. We modeled them all. And we included operational and embodied emissions. The model we used was what's called a top-down model. So we didn't model the number of buildings, we modeled society and how that impacts the number of buildings. And I'll talk a little bit about that in a minute. And we wanted to look at, you know, what is the feasibility, the scale of pace, and the policy settings that can deliver net zero whole life cycle built environment by 2050. So the model was developed by Cameron Allen. It's called the ISDG Australia Framework Model. It's basically a stock and flow model, and we added a new built environment module to that. And what the built environment module does is, in a typical stock model, you say, look, there's 10 million homes in Australia, and we reckon there's going to be 15 million in 10 years' time, or whatever. So you model a number of houses. We didn't do that. We modeled the economy. So what we did is we modeled things like GDP, personal wealth, and other factors which we know impact the number of houses and how big houses are. So it relies on the fact that as people get wealthier, they buy bigger houses. So it relies on the socioeconomic drivers. Likewise, for commercial buildings, we didn't say there's going to be 10 million square meters of extra commercial buildings per year. We said the size of commercial buildings, or the construction rate of commercial buildings, will be driven by the service sector growing, by GDP and other factors. So it's really looking at socioeconomic factors and how that impacts the amount of growth in the built environment sector. We modeled 3 scenarios. The first one was business as usual. So we just said, look, current population growth, temperature increases, resource demands. We modeled a slow transition to electric vehicles. So we said 80% electric vehicles by 2050. We said 30 to 50% of buildings will be all electric by 2050 and 60% renewable energy by 2050. So assuming we carry on the pace we're going. Then we modeled two ambitious scenarios. Scenario one looked at lower resource demands, a quicker change to EVs. It looked at a greater investment, financial investment in energy efficiency. So we assumed 70 to 80% all electric buildings by 2050 and 80% renewable energy by 2050. Finally, scenario two was the hardcore ambitious scenario. So it was 100% electric vehicles by 2050, 100% electric buildings by 2050, 100% renewable energy by 2050. And the additional one we did is we added 30% of multi-story buildings were going to be built out of timber slowly over time. So 1% in 2021, 2% in 2023, 3% in 2024. So we built up the capacity of timber buildings in society. So the results are quite interesting because, as I say, the model is driven by socioeconomic drivers. So what we can see here, this is GDP in Australia, and you can see GDP is increasing. Then there's a dip. That dip is COVID-19. You can also see the GDP starts to curve off because the model acknowledges that GDP will slow due to climate change impacts on productivity around 2040. So we're factoring in those broader impacts as well. What you see here are, this is operational emissions of all Australian residential and commercial buildings. Up to 2020 is based on what's happened, and then from 2020 to 2050 is modeled, simulated. So in business as usual, there's going to be a reduction because we are decarbonising. In scenario one, we got down to 28 megatons of CO2. In scenario two, we got basically down to 0. So we got down to 3 megatons. Embodied carbon, business as usual, reduced down to 4.3 megatons, because what we're measuring here as well is we're decarbonising supply chains. We're using far more renewable energy. So the embodied carbon of concrete, the embodied carbon of steel is dropping. Scenario one got us down to 1.6. Now, interestingly, scenario two became negative. We got a negative embodied carbon. And the reason for that was the timber buildings. And what we were modelling is all the other materials were reducing in embodied carbon. But timber, we were factoring in the long-term sequestered carbon storage over time. So timber elements, trees obviously photosynthesize, absorb CO2, and we're considering that within the kind of long-term carbon storage of those buildings. So that gives us a negative number. Overall, this is embodied and operational emissions. Business as usual was 66.4 megatons, and we got down to basically very close to 0 with scenario two. And what we found is we could actually get down to negative total emissions with some tweaks to the system and the number of timber buildings we were building and some other factors as well. There were some limitations to this study. So firstly, we only considered 6 materials: timber, steel, aluminium, copper, concrete. I can't remember what the 6th one was. So we're not including necessarily all carpets, all the finishes, all the paint. And so the embodied carbon was a bit of an underestimation. But the other thing we didn't consider is reducing the floor area of housing. And I think that's a big consideration. And that's because a model assumes as people get wealthier, we buy and we build bigger houses. And that's an intrinsic kind of relationship. One thing that could have got that reduction down sooner, or it could have offset all those additional materials we didn't model, is if we start to build more compact, sustainable floor spaces as well. So look, in conclusions, what we found is net zero whole life cycle carbon could be possible for Australia's buildings. But what's key is there's no silver bullet. We need a combination of methods, a combination of systems, a combination of approaches, a rapid shift to renewables, electrification of buildings, ambitious investment in energy efficiency, and the use of biomaterials as well. And that future modelling and future research in this area needs to include not only more materials, but also build smaller, build more efficient, and build and retrofit first scenarios as well. And I think I am just about in time. Thank you ever so much.
Thank you so much for fantastic and significant talk. We have received some pre-questions during the registration process, and also I have seen some questions in the chat. Over to you.
Great. Yeah, we got a few questions. So some pre-submitted questions, which I'm going to answer for about 5 minutes, and I'll try and catch the ones in the chat as well. I might talk quickly. There's a lot of questions, so please bear with me. Chris Nunn asked, what is the single biggest action the real estate industry needs to focus on to dramatically reduce embodied carbon? This is a really good question. I'd say the single most, the biggest action we can do is to measure embodied carbon consistently. And we know we've had some challenges around that one. But at the moment, if you show me a building and you say it has a 700 kilograms of CO2 per square meter, I do not know if that's good or bad. No, very few people do. If we take a building and we give it to 3 different consultants and tell them to measure the embodied carbon, they could come up with 3 very different numbers based on different methods, inclusions and exclusions. So what we really need is consistency in measurement, and neighbours are doing a great job with that in the kind of pipeline. But that's a bit of a kind of cop-out response. What's the single biggest action real estate can do? Well, what I found in my research is there's no silver bullet. There's no one thing. It's very tempting to say switch everything to timber, but I think that's misleading. I think we need a suite of actions. I think we need to build smaller and more efficiently. We need to question every square meter. And here's something the real estate industry will like. Efficiency is sustainable. I'm convinced by it. Do we need that extra elevator, you know, or can we make people wait an extra 20 seconds to catch another elevator? The rules that govern the performance of our built environment have governed us into inefficient situations, inefficient solutions. We need to challenge that. We need to radically retrofit. We need to consider every existing building as valuable. So some shitty 1970s office block has got an intrinsic value. Doesn't matter what it looks like. It has an intrinsic, it's an investment of labour and emissions from 50 years ago, where we can and where we should save it and we should retrofit it. We do need a widespread switch to timber and biomaterials, and we also need to dematerialise. And I think this dematerialisation can be quite controversial. But I start to question, do we need to build so much redundancy into our existing structures? You know, there's pretty good research out there that suggests we over-engineer our buildings. And using contemporary digital analysis tools, we can really reduce down columns and beams and floor plates to really limit the amount of materials we need. Amanda Sturgeon also asked, how can the use of mass timber in Australia be increased as a solution for both carbon reduction and reforestation to create a sustainable and native forest industry? Now, I'm really passionate about timber buildings. I think they're not only beautiful, they smell great, but also they're low carbon. And I think in this narrative that we can plant trees in a sustainable way to avoid monoculture and increase our biodiversity, we can harvest those trees to turn them into long-term products, such as building components that last 100 years, not Billy bookcases from IKEA that last 2 years, long-term products. And we effectively use our construction industry, our buildings, as a carbon storage system. This is very alluring to me. And we're currently doing the opposite. With concrete, as I say, you heat up limestone to create clinker that intrinsically releases CO2. Trees and biomaterials intrinsically absorb CO2. My only concern with timber is this, is you get some quite counterintuitive results in the analysis. I spend a lot of my time doing carbon calculations on timber buildings and timber products, and you get some weird effects. So some EPDs, for example, for timber show a higher embodied carbon for timber being recycled at the end of its life rather than going to landfill. It's quite a complicated reason for that, but effectively, if you recycle a product, say timber, at the end of its life, the benefit of that timber moves on to the next product. So it takes the sequestration with it. Whereas if you landfill timber, you put a piece of CLT in the ground, it will stay in the ground for hundreds of years. It will decay a little bit. I think you lose about 8% of the carbon over 100 years. Typically, it will decay a little bit, but it will effectively stay in the ground. So what we find is this kind of weird scenario where landfill is the best thing to do with timber at the end of its life, at a building scale, whereas at a societal scale, it's the best to recycle the timber. And I think we effectively, this is quite an immature area of analysis, and we need to develop better methodologies and mechanisms and analysis tools that credit the benefits of timber in the right way. I think there's about 10,000 questions now, so I'm going to rock it through. So Jeremy, as I said, it feels like structural engineering is much more conservative these days, resulting in excessive structural mass. Also heavy hanging cladding onto concrete frames. Absolutely. There's some research coming out of the UK led by Tim Orr, I think, where they're really questioning, do we need all this structure? And how do we balance safety? Because we can't have unsafe structures, and redundancy, because we need redundancy in structures. And if a column collapses in a blast or something, we need to build in that redundancy with efficiency. And so I think we need to fundamentally question how big slabs need to be, how big beams need to be as well. Tim Williams has said we need to design out the use of concrete. Absolutely, I have heard plenty of climate scientists say we effectively need to get rid of concrete. I don't know how I feel about it. We need to use far less concrete, I think. I think we need to use far less of it, and we need to move towards cement replacement materials, geopolymers. We're starting to get innovative carbon absorbing cement as well, which is quite interesting, although they're far from commercial reality. But I think 2020, 2021, 2022, people have started to take embodied carbon really seriously. So hopefully we'll get the supply chain changes soon. Sharon Francis has asked, do I know what the cost differential of the various material options is? We did in that paper. We not only looked at the embodied carbon, we looked at the cost as well. And we did find that timber building was cheaper, but that's just based on material costs. In reality, anything that's innovative costs more money. And so timber buildings are costing about 10% more, I think. Kenneth has asked, is the proposed use of timber ecologically plausible and sustainable? The Royal Institute of Chartered Surveyors say you can credit the sequestered carbon, so the really big carbon benefits of timber, if it comes from sustainable forests. There's a concern that if we all switch to timber, all of a sudden, there's not enough timber out there being sustainably harvested to meet that demand. And then you might end up with some unsustainable timber harvesting, which effectively sustainable timber harvesting means you don't reduce the global biostock. So for every tree you cut down to make into a building product, you plant a new tree. So effectively the world's ability to absorb CO2 doesn't change, you're just locking it into a product. There's some forestry where if you cut a tree down, there will not grow a new tree. And so that's not sustainable. And if we do that, it could, we found that some timber buildings could have a higher embodied carbon than concrete buildings if it's unsustainably managed. What are the longevity and risks associated with biomaterial? A worry about termites and boars in some Australian regions. I'm not sure, but we do have a PhD student, Florence Wong, looking into that. She is looking at mass timber in hot and humid climates. And not really from a material science perspective, but really looking at what are the barriers to mass timber in places like Southeast Asia, where there is huge amounts of construction going on. And so I don't know exactly the answer to that, but it's a really good point as well. Elena has asked, for scenario 1, 90% EV by 2050 seems really ambitious. Absolutely. What considerations were given to raw material access, and especially to lithium, which isn't readily available to cover all the automotive industry? I'd have to check, I can't remember in the model, but yes, certainly that scenario 1 and scenario 2 were really ambitious. They were very ambitious, and they would require dramatic policy changes as well. And this is why reducing energy is always better than just carrying on, because you don't need to rely on things like lithium. If we take a building that's using 100 kilowatt hours per square meter and reduce it to 50, we need no lithium to do that. There's a few of, I think I've just trying to check if there's anything that stands out. Are we running out of time, Lan?
Yes, perhaps you pick up the last question. For the remaining questions, we can email your answers to them.
I can actually do it. Let me do one more question. One I can answer. Is bamboo plausible to address biomaterial construction? I think that's I think we're going to see some real innovation. I saw something the other week, not so much bamboo, but bamboo laminated timber, effectively. So taking bamboo, cutting it up, gluing it together. Now the glue has VOCs and it's quite high embodied carbon, but you can now get sugar glues as well. So a combination of bamboo and sugar glue could be really interesting. We're also seeing things like the move, not only CLT and glue laminated timber, but dowel laminated timber, DLT. So instead of laminating things with glue, we can laminate with little dowels. We are at the cusp of real material innovation, which I think is really exciting in our industry. I'll try and answer everyone's question by email. It might be a long weekend for me.